Yeah, thank you very much, Marco, and also thank you very much to the organizers of this workshop for giving me the opportunity to give this talk. Yes, I will be talking about numerical methods for mixed boundary value problems, for diffraction problems. I will not be talking about homogenization problems. I was a bit over-optimistic when I submitted my abstract. So this is the homogenization part is currently work in progress. So I decided to focus only on diffraction problems. Okay, so this is a joint work with my postdoc advisor, Professor Stefan Llewellyn-Smith, which is who was the main organizer of this wonderful 4-month program at the Newton Institute. Okay, so what I'm going to do is to, I'm very lucky because I had we had Anastasia earlier giving an introduction on the Wiener-Hopf method, which is associated with these mixed boundary value problems that I will be talking about. So I will briefly talk about the Wiener-Hopf method, and then I will show you the diffraction problems which have motivated the development of these numerical methods, and then I will talk about the numerical scheme in more detail and then show you some applications and then discuss possible extensions of this work. Okay, so so we are interested about diffraction problems, and here I'm just showing some pictures that I found on YouTube. So we are interested in trying to compute the diffraction of waves by semi-infinite plane. And specifically, we're interested in developing numerical methods for dealing with diffraction problems with having mixed boundary conditions on this semi-infinite plane. Okay, and then these problems they lead to these Wiener-Hopf problems, and I should say, Anastasia told about this earlier, but I should say that, in general, we have to solve these Wiener-Hopf equations where, phi plus and phi minus are analytic functions in the upper and lower half plane, and then these functions A, B, and C are some functions which are known, and this functional equation is valid on a strip in the complex plane. Yeah, so what we want to do is to find a method to compute these functions, these plus and minus functions. And related to what I'm going to talk in this later, I should say that the behavior of these functions for large alpha is set by the behavior of the physical variables near the origin. And in this equation, this unknown function phi could be scalar, vector, or matrix. But for scalar problems, there's an explicit solution based on the Cauchy integral formula. But for matrix functions, for matrices, this equation can be solved in some special cases. And here I'm just showing some studies which are basically for matrix problems, and some of them are related to this, what I'm going to talk in this talk. Okay, so the problem which has motivated our work is, as I mentioned, this diffraction by a semi-infinite plane. So we have this semi-infinite plane here, and we have incoming wave at an angle θ naught, and I'm using C1 and rho 1, C2 and R2 in the upper and lower half planes respectively. So these Cj's are the sound speed, Rj's is the density. So we are assuming that we have two different media in the upper and lower half plane, and then we're also assuming that on top and bottom sides of this this semi-infinite plane we have different boundary conditions. So the governing equations are the Helmholtz equation here with this parameter here k, and then we can say that the total field is equal to the incident field, related to the incoming wave, plus the scatter potential here. And there's also time dependence which is only needed to determine the branch cuts related to the solution of this problem. Okay, as I mentioned, on top and bottom sides of this half plane, we can have different boundary conditions, and I'm considering this condition here, which has this general form. So if lambda is 0, if this parameter lambda is 0, then we say that we have an acoustically hard plane. And if lambda tends to infinity, then we have a soft plane. And also near the origin, we know that this the total field has, I mean, if we do local expansion, and we can write it in this form here, where r and theta are these standard polar coordinates. And doing local analysis for different boundary conditions, we can find the local behavior near the origin. So here I'm showing a table of all the possible cases. So if we have hard boundary conditions and then same medium in the upper and lower half plane, then near the origin we expect we can show that we have a square root singularity. And then this is a classical Sommerfeld problem. And also for soft, we can also do the same. We can also find the same structure. So if we have soft and hard, then we get a quarter, and then this problem was analyzed by Rollins. Same impedance boundary conditions on the top and bottom. We have again square root behavior near the origin. Different impedance boundary conditions, again square root behavior. But then if we have soft and hard, and then different media in the upper and lower half plane, then we get this more complicated behavior near the origin. And then this problem was analyzed by Wickham and Abrahams. So in this talk, I'm going to focus on the case of having square root singularity near the origin, but also I will also discuss on how to generalize to the quarter case, and then maybe possible extension to this more complicated behavior. Okay, so all these problems that I showed you, the table of problems, all these problems lead to either scalar or matrix Wiener-Hopf problems. And we know that Wiener-Hopf problems are related to Riemann-Hilbert problems. And what I mean by that is, I mean, a Wiener-Hopf problem is that functional equation that I showed you earlier, which is valid which is valid in a strip in the complex plane. So a Riemann-Hilbert problem is the same functional equation, but now it's only valid on a contour gamma, in this case, on the real axis. So we will exploit this connection between the Wiener-Hopf and the Riemann-Hilbert problems, and to see how we can solve the Wiener-Hopf problems by solving corresponding Riemann-Hilbert problem. So our work is based on the work of Olver and this paper here, and also Trogdon and Olver, this book. And I'm sure that both Tom and Sheehan will be talking about the numerical methods later this week. I think they're giving 3 master classes. So these two people have developed accurate and efficient numerical methods for solving Riemann-Hilbert problems. So we are going to build on their work to see how we can solve these diffraction problems with this more complicated behavior near the origin. Okay, so what we want to do is to develop, to present a numerical scheme for solving this equation here. In our case, we are interested about Wiener-Hopf problems which are valid on a strip. So we consider having this same equation but valid on the real axis. And so our aim is to find a function phi which is analytic everywhere in the complex plane, both in the upper and lower half plane, and which has this jump on the real axis. So what we are going to do following Trogdon and Olver, we say the following. So we represent this function by this series here as an expansion of Chebyshev polynomials with some unknown coefficients here, UK hat. And then, so we are thinking that, so this variable here, x, is a variable in the unit interval. So we are thinking of a map from the unit interval to the entire real axis, and we denote this by m, map from the unit interval to the real axis. And then in this case, so we can just substitute this expression here back here. So we can write this expansion for phi as this sum of Chebyshev polynomials with respect to the alpha variable. So this expression here, I mean, phi could be scalar, vector, or matrix, and obviously the coefficients will be of the same form. And I mean, from this expression here, then we can, applying this Chebyshev operator, I mean, following Trogdon and Olver, we can compute these coefficients using this relation here. So yeah, so what we have done to this point is that we are trying to solve this equation here. We are representing this phi function along the real axis, but by representing it on the unit interval using this mapping idea. So and then next we see collocation method, where now this function, this phi representation, we are going to evaluate that and evaluate the functional relation along some collocation points. And in this case, we choose these Chebyshev points of the second kind on the unit interval. And then, so we have these points on the unit interval, and via the mapping, these are mapped to the entire real axis. And then the collocation method is based on computing the Cauchy operators acting on this function phi. So I mean, the Cauchy operator is given by this expression here. So it's just, I mean, we denote it by C phi, given by here. So if we want to compute, I mean, if I go back, so we want to compute phi plus and phi minus. We have a representation for phi. So what we want to do is to compute the Cauchy operator acting on this function on the two sides of the contour. And so what we want to do is to, I mean, construct the collocation method. We are computing these matrices, C plus and C minus, at the points which correspond to this collocation, collocation points coming from the points on the unit interval. So, I mean, and since these C plus and C minus operators are related like that, by this expression here, it's sufficient to construct only one of those operators. So what we do is that we have the representation for phi, so we apply the Cauchy operator on that function, and then if we do that, that means that we are basically applying the Cauchy operator on the Chebyshev polynomial. So if we do that, we get this expression here, and then using just this notation here, we can write it in this form here. So this expression here, this is a Cauchy transform of function phi, but up to a constant, because here we are not saying anything yet about the far field behavior of alpha. So, and in our case, our contour of interest is the entire real axis, so we must put into our solution scheme all the information about what is happening at infinity. So, yeah, so here we are just computing the Cauchy transform of phi. So let's now use that expression, but evaluate it at all those collocation points. So collocation points, we are denoted by xp. Via the mapping, they are mapped to some other points, alpha p on the real axis. And then we are just substituting those points, and then also substituting the expression that we had for the coefficients. Then, I mean, doing some analysis, we can find an expression for the Cauchy transforms as a matrix, and where alpha q are all those points on the unit interval on the real axis, multiplied by the CPQ matrix, which contains all the Cauchy transforms of those of the Chebyshev polynomials, evaluated at all those points. So what we are going to do, what I'm going to talk next, is that we are going to consider mappings which have multiple inverses, especially rational mappings with, let's say, D inverses, which means that if we want to do this procedure of computing the Cauchy transforms, we need to do that for all the inverses of the mapping. And also because our contour gamma, in our case we are solving a problem on the real axis, is unbounded and has the two preimages. Preimages are the two endpoints of the unit interval. We also need to we need to take account on all the limited behavior for for large alpha. I mean, so we need to make sure that we have the correct behavior at those points. Okay, so so this is what I just mentioned, that we will be considering we consider these rational mappings, and we will be computing the Cauchy matrices for these rational mappings. And the reason we are computing these, we will be considering these rational mappings, is because these will help us. These are basically will basically be taking into account what is happening near the origin, the square root singularity that we want near the origin. So, I mean, let's initially consider this 2-to-1 mapping, a mapping from the unit interval, minus 1 to 1, to the real axis. And then this mapping, this has two inverses, which are given by this expression here, these two expressions here. So, both the unit interval, the unit interval is mapped to the real axis, but also the minus 1 over x outside of the unit interval, minus 1 over x function is also mapped to the to the entire real axis. So, which means that we need to construct Cauchy matrices for both inverses. And also, I should say that this rational mapping is a not function of x, meaning that the infinity has two preimages, which is exactly what we want, because we want to have mapping from the entire real axis to mapping from the unit interval to the entire real axis. And I should say that the minus infinity and infinity correspond to these 2 points, minus 1 and 1, which means that at those points we need to make sure that we have the correct behavior. So, as I said, for each of those inverses, we have a contribution to the Cauchy matrix. So, two inverses. So, we have C1 and C1 plus and C2 plus. So, the form of these functions, I think Tom and Xian will discuss about that later this week. We have these two contributions, but then we need to subtract some other values which will ensure that the behavior at the endpoints of the unit interval is correct. So I should say that let's say near one of the endpoints, near 1, x equals 1, then the mapping has this form here. Similarly for x being near to minus 1. And then for the diffraction problems that we're interested, this function that we're looking for has this square root behavior near the origin, which means that if I use this mapping and I have this local behavior, then if I take the minus square root of that here, then I have something, I have this I have 1 minus x to the minus a half, which means that if I represent my function using this mapping, then I do not expect to have a spectrally convergent Chebyshev series in terms of x variable. So, but what we can do is to consider a 4-to-1 mapping, which let's say has this form here. This mapping has 4 inverses, shown here. So, you have x, 1 over x, and then these points along the unit disk. All these are mapped to the real axis. So, but now, if we do a local analysis near, let's say, point 1, then we see that alpha, so if I just go back, so this mapping here, if I just do some local analysis near 1, I get this behavior here, which means that if I take minus square root, then also take a minus square root of that, then we see that if we use this mapping, we expect to have spectrally convergent Chebyshev series. So in this case, we have four inverses, so we need 4 contributions in this Cauchy matrix. So we have C1, C2, C3, C4 plus. And then again, we need to subtract some expressions here, which will ensure that we have the correct behavior near the endpoints, which correspond to infinity. Okay, so let me now show you some applications of the method. First problem, we consider the classical Sommerfeld problem, where we have same medium in the upper and lower plane, and we have hard boundary conditions and on top and bottom sides of this semi-infinite boundary. So, just skip all the details. So in this case, the problem leads to a scalar Wiener-Hopf problem, which has this form here. So we're trying to find this plus function. This is a known quantity here, and then d minus is the unknown function, and then gamma is this square root expression here. So scalar problems, this has an explicit solution. So this is the equation here. So what we do, we just divide by gamma, by this function here, without loss of generality, and then take this expression here, and then substitute, replace phi plus with c plus phi, and then the same for d minus. So rewriting this expression here as a matrix problem, we can write it like that, where m is given by this expression here, n is given by that. So we just solve this linear system, and then if we want to compute phi plus or phi minus, we just apply the c plus or c minus operators on the solution of the system. Okay, so here I'm just showing you some errors where now we are computing. So these are different norms. So let's just focus on the first one. So these two points, these two series of points here correspond to error when we use the 2-to-1 mapping, and then we see that the error is not very good because, as expected, the mapping is not able to, the numerical scheme is not able to capture what is happening near the origin. But if we use a 4-to-1 mapping, which takes account of the square root singularity, then we get that for this number of collocation points, we get spectral accuracy. Then here we are just comparing expressions of these sectional analytic functions, phi plus and d minus, with the exact solutions. But that was for the scalar problem. But the numerical scheme can be applied to solve matrix problems. And one matrix problem is this so-called seniors problem, where we have same impedance boundary conditions and on top and bottom sides of the half plane. So we have conditions of this form here. Same analysis leads to these two coupled equations, where now we are solving. So which can be rewritten in matrix form here, and now we are trying to find these two these two vector functions, phi plus and phi minus. In this case, it turns out that if you add and subtract the equations, it leads to two independent scalar problems. But let's just consider the matrix formulation. Same story. We just rewrite it as a linear system, solve the linear system, and then if we want to compute phi plus or phi minus, we just apply the operators on phi. And again, here we are computing errors, different norms for these different sectionally analytic functions, phi plus and phi minus. Here we are comparing our solution to highest resolution numerical solution. And then finally, I would like to talk about the Hilbert problem. Not giving any, I'm skipping that part. So the Hilbert problem concerns the same diffraction problem, but with different impedance boundary conditions on top and bottom sides. So we have these conditions on the boundary, and then this leads to a matrix Wiener-Hopf problem of this form here. So again, this is a matrix problem. We're trying to find phi plus and phi minus. Solving this problem, again, we can get some, we get the errors for these, all these sectionally analytic functions. Okay, so I would also like to say that with the solution of the numerical, of the linear system, we can also compute all the quantities of interest, all quantities of interest. In these diffraction problems, we are interested about the far field directivity, and then this is the field, which as r tends to infinity, we can rewrite it in this form here. So, and then the far field directivity d theta is defined like that. So here I'm showing the far field directivity for the Sommerfeld problem, the Senior problem, and the Hertz problem compared. I mean, the solid lines are the exact solutions, and then the dots correspond to our numerical solution for different parameters, and you see that the two the solutions agree. And we can also use the solution to plot scatter field. So here we are showing the scatter field for the Sommerfeld problem for different distances from the origin. And for, I think the diffraction parameter was 1, and then the angle of the incident wave was pi/5. So again, solid lines, exact solutions, and these small circles are the numerical solutions using 129 collocation points. Okay, so let me just summarize. So what we have shown is that we can solve Riemann-Hilbert numerically using techniques based on Fourier and Chebyshev transforms and conformal mapping following Olver and Trogdon, and Tom and Xian will be talking about these, the methods that they have developed to solve Riemann-Hilbert problems. They will be talking Wednesday, Thursday, and Friday. So we saw that this, the idea of using these rational mappings with multiple inverses was help us to capture the square root behavior near the origin, and which was associated with hard or impedance boundary conditions. So if we want to do more complicated structure, for example, if we want something, consider the Rollins problem where the behavior near the origin was a quarter, then in that case we can consider an 8-to-1 mapping. And also some future things that we can do is to adapt to solve problems in more complicated geometries. For example, scattering by wedges, elasticity problems, and then also the Wickham's and Abraham's problem where near the origin we have more complicated behavior near the origin, and as I mentioned was alpha in that case is given by that. In this case maybe we can consider expanding in terms of Jacobi polynomials, and also something that Anastasia also mentioned is to extend to Wiener-Hopf problems with matrices having also exponential factors. So I would like to end by acknowledging discussions with David Abrahams, Matthew Colebrook, Anastasia Kisil, Martin Xian Olver, Matthew Pridin, and Tom Trogdon. And yeah, thank you very much. No, we didn't.
That's relevant for the other problems.
Yeah.
Because you don't have, you possibly cannot completely get rid of it. The same trick.
Yeah.
So you probably need the singularity subtraction.
Yeah.
If you have done 4 or 5 of them, it will be just as good.
Okay.
How do you know that your problem with attacking numerically has solution at all? It could be many solutions, it could be some finite or even infinite number of conditional solvability. I don't see how that technique may happen.
I mean, yeah, so, sorry, this one here. So here we just, I mean, the solution we checked against exact solution which was valid for the far field directivity, and these methods agree. So I would assume that that was enough to show us that, yeah.
Problem is the problem we discussed because
Yeah.
is known as
Yeah.
unique, but in the conclusions
Yeah.
you listed very different goals for calculating everything, and those, especially the last problems and some other problems for last waves and so on. Are they quite sensible? I mean, I didn't see any random number or index of the problem here.
Yeah, I'm aware about those things, but I don't know. I mean, I'm aware, but I don't know many things about the also the partial indices and those things. Yeah. So I just listed some problems. So at least for the some of them we have thought about possible directions, but I mean, whether the solution would give something which is not valid, I don't know. I mean, I expect that should be okay, because I mean, you are solving it's a linear algebra problem, so I would expect it to be okay.
Stated another way, how, I mean, basically, you are looking at control of what you're calculating versus what you are not calculating.
Yeah.
So it's a matter of rigorously controlling that. And the cases where you don't have, where you have conditions, you probably practically would show up in very nearly singular matrices.
Hmm.
So that would be
Okay.
one.
Yeah.